Now that we've developed a subring test to see when subsets of rings are themselves rings, we're going to come up with another subring test that'll be a little bit easier to prove. So first we're going to determine and prove the test, and then we're going to apply it to an example to show how it's a little bit easier than the first version of our subring test. Alright, so first of all I want to recall the subring test that we have already proved, that we proved in the last video. And that is if you have a ring R and a subset S of R, then S is a subring precisely when S is closed under addition, closed under multiplication, the zero element is in S, and it is closed under additive inverses. And we found this test, remember, by just taking the properties of a ring and focusing on the ones that weren't automatically true because of the addition and multiplication in the ring R. So the question you might ask is, can we get a test with fewer things to prove? And if you're looking at closure under addition and closure under additive inverse, you might think that subtraction is a good place to look, because subtraction is a combination of addition and additive inverse. So if I want to do x minus y, that's the same as x plus a negative y. So perhaps having some kind of closure under subtraction could give me closure under both of those operations. It's worth a try. Let's see what we can get. So let's see. So suppose R is a ring, and suppose S is a subset of R, and suppose that S is closed under subtraction, and let's see what we can get just by that one assumption. So if we take an element in our subset S, well, we know it's closed under subtraction, so right away, just with that element S, we know that when we subtract X from itself, that has to be an S. Well, guess what? X minus X is equal to the zero element. That tells us the zero element is in S, which is a little bit of a surprise, right? We weren't even expecting that. We were looking at addition and additive inverses, and it turns out that the zero element is also in there. Let's see what else we can get. Well, that tells us that S has an additive identity, so that's great. So now we have two elements. We have that X from the original one, we have the zero element R, and again we still have closure under subtraction. So what happens when we subtract 0R minus X? Well, that's going to be an S, but when we do that, what do we get? We get negative X is an S, so that means we have closure under additive inverses. So we have closure under additive identity, closure under additive inverses. Those are two of the properties that we need to prove under the old subring test. And if we have X and Y in S, let's see if we can get addition, right? So now we just proved that we have closure under additive inverse. So that means since Y is in S, that means negative Y is also in S. And that means when we take X plus Y, which by the way is X minus a negative Y, since X and negative Y are both in S, and since we have closure under subtraction, that means that is also an S. So we get three properties from one. We get the zero element, we get closure under additive inverse, and we get closure under addition. And so we think, okay, well, that means all we have to do is prove closure under multiplication, and we're in good shape. However, in doing all those computations, and doing all that reasoning, there was a hidden assumption that we had that we didn't state explicitly. And that is, we need S to be non-empty. Go back to that very first, let X in S. We can't say that at all unless there is actually an element X that is in S. So we need that additional S is non-empty. But once we have S is non-empty, we get those three properties. That, along with closure under multiplication, will give us that the subset is a ring. So here's our subring test number 2. Let R be a ring, let S be a subset of R. Then S is a subring of R precisely when these three things are true. First of all, S is not empty, S is closed under subtraction, and since both of those things give us the zero element, closure under addition, closure under additive inverse, and an additive identity, all we have left is to show that it's closed under multiplication. All right, so let's look at our old friend, the set of multiples of 4, and we've already proved this is a ring using the old subring test. Let's see how it works with the new subring test. All right, we're going to prove S is a ring. So S is a subset of Z. We just have to prove that S is a subring of Z. So we're going to use that subring test. So we need to prove three things. First of all, S is non-empty. And for that one, just choose any element in S that exists that you like. Well, you know my favorite. My favorite is, of course, going to be 0, which is 4 times 0. 4 times 0 is an S. Even if that wasn't 0, it would still be an element of S. So it's non-empty. Closure under subtraction. Well, let's see. Let A and B be elements of S. Show that when we subtract them, they're also an S. This is going to be very similar to closure under addition. So A is a multiple of 4, B is a multiple of 4. When we subtract them, we get 4m minus 4n. We can still factor out that 4. M minus n is still going to be an integer, so that means that A minus B is a multiple of 4 and therefore is an S. And then finally, closure under multiplication is similar to last time. That one you can check pretty easily. And those are our three properties. We're all done. That means that S is a ring. All right, so go ahead and try this version of the subring test on the PDF file included with this video. It's actually the same one as for the last video, same subrings. You're just going to apply a different subring test to them.